Hi, this is my English speaking practice, and I'm working on coding programs. And today I'm gonna solve this populating next right pointers in each node. Yep. And today I've I've had I've had I've had mock tech interview. Yeah, and yeah, I did I did it well. So I'm keep going. Yep. Go back to the problem. You were given a perfect binary tree where all leaves are on the same level and every parent has two children. The binary tree has the following definition. Yep. Next. Okay. Populate each next pointer to point to its next right node. If there is no next right node, the next pointer should be set to null. Initially, all next pointers are set to null. Oh, I see. Okay. So given the above perfect binary tree, figure A, your function should populate each next pointer to point to its next right node, just like in figure B. The serialized output is in level order as connected by the next pointers with sharp signifying the end of each level. Okay. Recursive approach is fine. Okay. Let's work on. Yo. So I will visit every node and at the same time find the next node to it. If it's the left child, it's easy because the next node would be the right child. Okay? So it's sibling. Yeah. But this case is difficult because yeah. If I do DFS, depth first search, cannot see the node that has different parent nodes. Okay, so let me think about this. Yeah, if I can use extra space, I will use hash map and the level for the key and node for the body. Yeah, but follow-up questions, we may only use constant extra space, so we cannot use hash map to store the level and node. Yeah, so what we should do is to identify the level with constant extra space. To identify the level of the nodes with constant extra spaces. Yeah. But the key thing here is perfect binary tree. There is a perfect binary tree. So 0, 1, 2, 3, 4, 5, 6. 0, 1, 2, 3, 4, 5, 6. Yeah. We 0, 1, 2. Yeah, we can get the index. We can calculate. We can figure out the index of the node. So this case 5 is the next point to 6, and we can know we can know where the next node is. So I should use this. I should use this property, this feature, or this characteristic. I don't know, but perfect binary tree is a key thing here. So I will use DFS and have to manage the index. So the first one is 1, and left child index of left child would be 2, and index right child be 3. This is obvious. How about this? 2's child are 4 and 5. 4 and 5. And 4's child be 8 and 9. 5th child would be 10 and 11, 12 and 13, 14 and 15. So there is a pattern. Doubled, the left child index of the left child would be doubled, and the right index of the right child would be doubled plus 1. Okay, so Uh, but how to update? For example, in DFS, when we visit this node, we can access the parent node and the left child and right child. And that's it. So it's not easy to access this node. Parents next right, parents next left, parents next nose left child. Okay, parents next node left child, parents next node left child. I see. So when it's the right node, parents next node left child would be the next node. If there is nothing, we set it to null. That's it. So yeah, whatever the level is, the relation doesn't change. Parents node and go to the next node, and left child will be the next node for the right child. Yeah. I think so. So I will use DFS to traverse the perfect binary tree. So it takes node and it's optional. Node type. Okay. And node if it's none, we do nothing. And we should get parent node. Okay, parent node. Yeah, that is. Oh, I see. It should be given. And we know the parent and the parents next. Yeah, we can assume parent node is already updated, so it have next pointer, so we can get next node. It's kind of uncle or aunt or something like that, the sibling of the parent node. Yeah, next node is Yeah, we can get next node. Wait. We should know about whether the node is left child or right child. And if the current node is right child, we should know the next node. Sorry, my bad. Parent, we should know the parent's next node. M. Okay. And if not none, we can get the next node, and it might have left child, and we can update the next to the left child. Left child might be none, but it's okay. Next should be, yeah. Oh, but there's no case. Yeah, it's impossible that the left child is none because the tree is perfect binary tree. So if the current node exists, and the parent's next node exists, left child should exist. Yeah, we can update the next field, next pointer, right? And next, if it's left child, we just update parents right. Yeah. And after that, if there is left child, we go left, parent is not itself, and its right flag is, yeah, false. Otherwise no. And then likewise, yeah, we do the same for right child. That's it. And return the node. For the first, for the first it's right, it can be handled as right child. Okay. Parent might be noun. Great. Great. Let me submit it. Okay, not bad. Not bad. Let me see the fastest answer. But this answer use extra space, so yeah. My answer is good. Less memory. Okay. Okay, next. I will go for speed today. So next, similar one. Populating next right pointers in each node 2. Given a binary tree, populate each next pointer to point to its next right node. If there is no right node, the pointer should be set to null. Initially, all next pointers are set to null. So this time, okay, I see. And that the tree is not perfect, so just binary tree. So there is there is no node. Okay, and that a follow-up question. You may use only use constant extra space, and the recursive approach is fine. You may assume implicit stack space does not count as extra space for this problem. Okay. It's getting more difficult. Okay, so the difference is, the tree is not perfect. So when we get empty, we should go next. Yeah, but how about this case? Okay, I see. Oh, I see. So it's not so complicated because yeah, for it's same for go parents and it's next go to the parents and go to the next node of the parents and yeah. Mm, oh wait, but that when we think about the children, right children of the node 5, and let's assume 6 exists but it doesn't have any child. In this case, we can go to parents node and its next node, but it doesn't have any child. So in this case, we should go next. So basically, go to parents and next and check it have any of children. If it is, we can identify, and if it doesn't, we go to next and check if it has children. Yes, that's yeah. Yeah, this is the idea I'm thinking about. So, and the time complexity is not too bad, and the space complexity doesn't change from the previous one, so space is good. But the time is also maybe since we have to visit all the nodes, so it takes n, it's a number of nodes, and additionally when we update the next pointer, it might be the max length of its level. So yeah. But it's but it's not bad because if we go if we have to go from the leftmost to the rightmost, it means there is no nodes between them. So we can know that is not bad. So basically it's the same as the every node in that level exists. Yeah. Does it make sense? I feel like I'm not able to explain this. So let me write it. the time complexity first we should visit every node, so it will be n, and where n is number of nodes. Okay, and additionally, when we update the next pointer of the node, we might visit yeah, but yeah, at the view of entire at the view of entire process, it means there is no node between right? So sorry, but it means so at the view of entire process, it doesn't change, it doesn't different. It doesn't different from the case. It takes m, where m is the number of nodes at the level, at that level. But it means there is no node between leftmost and rightmost, right? So at the view of entire process, it doesn't different from the case where the Difficult to say. There are nodes. We might visit the leftmost node to rightmost node at the parent level. It takes m. M is the number of nodes at the level, but it means there is no node between leftmost and rightmost. So at the view of entire process, for each there are nodes. There are nodes from the normal case. Okay. So after all, updating next pointer for a node takes constant time. Yeah, so the time complexity is, I think, n. DFS node optional node. It takes parent, that's optional, and the flag is right, and if node is none, we do nothing here, and if is right, is right. If it is right, should iterate, not iterate, should traverse parent and its next node. So the parents next, parent next would be parent next if parent exists, otherwise return none, and if parent next and from now it should be iterate through loop. It should loop because the parent next node doesn't have any children. So in that case, yeah. So the parent next, as long as parent next exists, we can get the left, and if left exists, we can update the current node's next field. That should be left node, and break this loop. Okay, and next, yeah, node next. Okay, and if there is no children left and right, we move on to the next parent. That means parent next would be the parent next. Yeah, and if it's none, we break it. So we couldn't update the next pointer anymore, but it's okay because yeah, the next pointer should be none, so we don't do anything in that case. That's it. And if it's left, if parent and parent right exists, we can update the we can update next pointer to the parent right. But otherwise, we have to do the same thing. So we can copy this. Because there is no right child, we have to go the parent's next node and check its children, and process it in the same way. That's it. And after updating the current node, we have to call DFS, and node is okay. is right. How about this? Wrong. Yeah, we should return node. Okay. Not bad. Let me see the result. Okay. 1, 2, 3, 4, 5. In this case, we can handle it. But why? It's left child, so check if parent right exists. No, so we go for the parents next. Okay, and parents next doesn't have left and right child, so we go I see. At this time, when we are looking at 7, node 7, the 5 is not updated at the time because it's DFS, so the 7 is found first. So that's a problem. So how about go for right first? This case we can update this and 1, 3, 6, 8, and after that we look at 2 and we update it, and then we go for 5, node 5, and after that we go for 4 and 7. Yeah, I think this is good. Great. And that's cool. So let me see the result. Yeah, not bad. So the coding is good, but I'm curious about my English works or not. So let's have it reviewed. Okay, here's the thing. We want to set the next pointer for every node to the next right node at the same level. If there's no node, we just leave it as none. The time complexity is basically O of n. We visit each node once, and even when we check neighbors across the level, it doesn't add extra asymptotic cost. So yes, still O n. Is this let's break this down carefully, both technically and grammatically. Your original comment is mostly correct in spirit. You visit every node once, so O of n. Finding the next right node may involve scanning across nodes as the parent's next pointers, but in total, across all nodes, this still sums to O of n because each node is effectively visited once when setting someone's next. So technically, yes, it's correct, though your original explanation is a bit confusing to follow. Phrases like "it means there is no node between leftmost and rightmost" are not clear in the technical sense. Every node should be every node. Additionally is typo, and at the view of entire process, awkward, better. In the view of whole process, it doesn't differ. I see. Some sentences are long and confusing. Breaking them helps readability. First, we visit every node once, so that's O of n, where n is the number of nodes. When we update a node's next pointer, we might have to look across nodes from leftmost to the rightmost at the parent level. But over the entire process, each node is still effectively visited only once. So overall, setting the next pointers takes yeah, but this differs what I wanted to say actually. So let me explain it in Japanese. NEXT ポインターを更新するので、基本的には O of n になります。追加で更新時に NEXT ノードを見つけるためにための操作があります。その際に親レベルでそうですね、親レベルで一番左から一番右までポインターを NEXT ポインターたどっていくことがあります。これはそのノードのそのレベルのノードの数分のステップがあります。しかしその場合っていうのは高レベルにおいて一番左から一番右まで、ノードがないという状況になっています。つまり、ここで言いたいのは全体で見たときにON に加えて、追加の時間計算量がかかるということはないということ、かからないということです。平均というか、なんていうか、平均というと語弊があるな。一つのノードは定数時間で更新できるとみなすことができます。ちょっと日本語でも説明が下手だな。結局ノードを一個一個見るのと変わらないっていうことですね。左から一番右までの NEXT ポインターをたどるっていうことは結果的に、全てのノードがある場合もその親レベルでの、全てのノードがあったとしても一個一個を見てみると一個一個のプロセスで全体で見てみると、 結局一番左から右までの親のネクストポインターをたどるっていう処理は存在しているから変わらなくて、で1個のノードを更新するときには、パーフェクトバイナリーツリーだとして、親見て NEXT 見てその子供を見るという定数時間で更新できるため、最終的には ON ですね。Here we visit each node exactly once and update its next pointer, so the base time complexity is O of n, where n is the number of nodes. When we update a node, we might need to find its node pointer by looking across node at the parent level, from the leftmost to the rightmost node. That scanning takes steps proportional to the number of nodes at that level, but this only happens in cases where there are gaps at the child level, meaning there aren't nodes in between. So overall, across the entire tree, these extra steps doesn't add extra complexity, and we can think of updating each node as taking a constant time. Therefore, the overall time complexity remains O of n. Yep, each node is visitable, so finding the next node might involve scanning across the parent's next pointers, but the scanning only happens when there are gaps on the child level. So overall, even counting these scans, the time complexity is still O of n. In other words, each node can be considered updated in constant time. Yep. Yeah. Okay, so let's finish this problem. And I solved 1, 2, 3, 4, 5, 6, 7, 8. Yeah. I have to solve 2 more problems today. Yeah, my goal is to solve 10 problems. So, but I will go for dinner or more cheaper expression. Spar. Yeah.
Supper.
Yeah. Supper. So I will finish this stream, and after my supper I will go back and solve 2 more problems.